I want to look at a problem today where we take advantage of Hess's law to calculate the delta H of a reaction that we don't know the delta H for, using the information on delta H for several reactions that we do know delta H values for. So the reaction that we're going to look at and try to find the delta H value for today is this one. C2H4 plus 6F2 give us 2 CF4s plus 4 HF. The reactions that we're going to use are these three right here. We know the enthalpy of all three of the enthalpy change in all three of these reactions. And what we're going to do is we're going to look one reaction at a time and see what we have to do to each reaction in order to get it to conform, or I shouldn't say conform, I should say add up to the target reaction when we add all of our reactions together at the end. For the first reaction, you'll notice that we have F2, which is in our target reaction, and HF, which is in our target reaction. We're going to look at using this to get the HFs, because this is the only reaction we have an HF in. None of the other two reactions have it, whereas one of the other reactions has an F2 in it. So whatever we do, we're going to have to get 4 HFs out of this reaction. In order to do that, we're going to have to multiply this reaction by 2. So we take reaction 1 and we multiply it by 2. When we multiply reaction 1 by 2, not only do all of our chemicals get multiplied by 2, our reactants and our products, but the delta H value gets multiplied by 2. For the second reaction, again we have fluorine and we have CF4. And just like for the first reaction, while we have multiple reactions with fluorine in it, we only have this reaction with CF4 in it. So whatever we do, we're going to have to get 2 CF4s out of this reaction, because that's how many CF4s are in our target reaction. So we're going to take the second reaction and also multiply that by 2. And again, when we do that, we multiply our delta H, our enthalpy of the reaction, by 2. Finally, when we look at the last reaction, you'll notice we have C2H4 on the right side, on the product side, whereas in our target reaction, it's on the reactant side. So what we're going to do is we're going to reverse the third reaction. And when we reverse the third reaction, we actually have to take the negative of the enthalpy change for that reaction. So instead of being plus 52.3 kilojoules, it's going to be minus 52.3 kilojoules. Now we're going to add these reactions together. When we do that, there are a few things that we will cancel out. For instance, we have 2 H2s on the left side and on the right side. We have 2 carbons on the left side and the right side, so those both cancel out. When we add everything together, we get our target reaction. So we have the 1 C2H4. We have 4 F2s plus 2 F2s, giving us 6 F2s. And on the right side, we have 2 CF4s and 4 HF, giving us what we want. In order to get the enthalpy change for this reaction, we need to add all of these individual enthalpy changes. And when we do that, we get minus 2486 kilojoules.